All right, guys, so this video is mainly for third period students. For those students in third period, we were unable to finish the explanation of this worksheet. But if you're not a third period AB student, if you're another student, if you want to just listen in, fine. All right, in third period, we actually did get down to question 5 and 6, and we needed to talk about 7 through 10. But I do want to go back and look at 5 and 6 real quick with you guys. And it's just I can't put the graph on the screen along with the question, so I'm actually going to talk about 5 and 6 and put them right here. All right, 5 asks you, when does the body speed up? So we're looking for where speed is increasing. Just a note for myself. And this is where is speed decreasing? Because you're asked, where does the body slow down? All right, we work in our physics brain for a minute, and what you maybe remember from physics. If you're looking at a velocity graph, what's happening is we work our way from 0 over here to 10. Okay, on each of these pieces here, we can see that from 0 to 1, the velocity graph is moving away from the x-axis. Well, you would have said that that's an interval on which the graph is, the body is speeding up. So 0, 1 belongs here. And let's think about it for just a minute. We're not going to use an explanation of because velocity is moving away from the x-axis. One of the two correct explanations, justifications, and calculus is because speed is increasing because the velocity is positive. This whole part of the graph is above the x-axis, and velocity is increasing. Okay. Velocity is positive at each and every one of these time values, but successively on that interval, it's increasing. So you could say velocity is positive and velocity is increasing. And notice I'm not writing anything down because I want this argument to come from not just velocity, but from velocity and acceleration. So velocity is a positive. Also, the acceleration, which is the slope to velocity, the acceleration is positive. So velocity is a rate of change. Acceleration is a rate of change on this body, this particle. Both these both these rates of change, derivatives are positive. They're working together. Okay, the particle's moving to the right with a positive acceleration. Well, that's just aiding it in going faster. So our explanation would be because V and A have the same signs. All right, so let's find another time when the speed is increasing. Well, speed is not increasing here, it's decreasing. So from this x-intercept that we've decided to call, I guess, 2.1 to the time of 3, we can see that the velocity graph from physics is moving away from the x-axis, so we know it's speeding up. Well, let's look at the justification in calculus. All right, well, the speed is increasing for us because velocity is negative and velocity is decreasing. That's one way to say it. Or velocity is negative and acceleration, the slope, is also negative. So on these two intervals right here, we can see that speed is increasing because A and V and A, have the same sign. These two rates of change, they coincide. Okay, another time where the particle is speeding up is from 7 to 9. For the same reason that the particle is speeding up from 0 to 1. So we also have to add 7 to 9. So if I asked you to justify, and I'm lumping all these together, this part of the graph, which are both positive, and this part, which is negative, okay, you're just going to simply say because V and A have the same signs. So this should just be on your blank for number 5. I just couldn't fit it on the same screen. All right, let's look at slowing down. Speed is decreasing. Your physics brains tell you when the velocity graph goes to the x-axis. So that would be from 1 to 2.1. Okay, but the calculus justification is about the signs of velocity and acceleration because V is positive, greater than 0, And v is decreasing, which means if the velocity is decreasing, the slope, a, is negative. Positive velocity, you're moving to the right, but your acceleration is negative. It's slowing you down. Okay. The other time that our particle is slowing down is from 5 to 7. Because the velocity graph in our physics brain is moving towards the x-axis. And also 8 to 9. Okay, let's look at the interval from 5 to 7. V is negative, but a, the slope, because velocity is increasing, a, the slope is positive. The velocity wants to go left, but the acceleration is saying, no, 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 I want to go in a positive direction to the right. So it's causing it some grief, and it's slowing it down. 8 to 9, for the same reason over here, positive velocity, but negative acceleration. These are the time intervals that the particle is slowing down because v and a have opposite signs. All right, let's look at question number 7. When does the particle move at its greatest speed? Well, I'm going to go ahead and produce the speed graph, and we'll answer that question when I do get the speed graph. All right, question 8. When does the particle stand still for more than an instant? Oh, that one's pretty obvious, I think. On question number 8, right here, 9 to 10, your justification would just simply be because v of t on that time interval is equal to 0. 0 velocity, not moving. All right, the final few questions is going to be 7, 9, and 10. So let's get 9 and we'll answer 7 and then we'll complete with 10. Okay, graph the body's speed. Speed is the absolute value of velocity. So looking back up here at my velocity graph, absolute value on velocity causes any portion of the graph that's below the x-axis to come above, be reflected through the x-axis, and be positive. So this portion of the graph is going to stay where it's at. So I need to reflect this portion, okay, through the x-axis. So I'm going to choose the point 3, negative 2. It becomes 3, positive 2. So that point down here reflects to here. Likewise, 5, negative 2 reflects to 5, 2. I'm going to try and complete the graph. So if I were to connect here, connect over, and then connect this way, okay, I've reflected the negative to the positive here. So I'm going to try and recreate that graph down here on my speed grid. All right, so I know from 0 to 2.2, the graph would stay as is. I believe that was 3. And then I think at 3, 2, the graph went something like this. This is 3. It continued horizontally to 5. I think it's 7. It joined back with the next intercept. It's 8, 9, and 10. And then I believe it went something like this, perhaps. Okay, where this y value I think was 1. I think it's not as steep if you look back at the graph. And then we have this. So let's answer question 7. When does the body, particle, whatever, move at its greatest speed? Well, if it's asking me a question about speed and I have a speed graph, I'm certainly going to use the speed graph to get an answer. When, at what time? T equals 1. That's the answer. At t equals 1, the particle moves at its greatest speed because you could say speed is a maximum at that time. You could say this is the greatest y value on the speed graph. A couple different choices, but I mean, you're simply choosing t equals 1 because that is the highest y value. That's it. Last problem. Let's graph the body's acceleration where defined. All right, well, acceleration is the slope to velocity. So they could have said graph the slope graph for this given graph. All right, so we're going to take, ignoring this green part of the graph here, the original graph, okay, we're going to go ahead and graph the slope graph. Notice this is a piecewise linear function. This graph is made up of a bunch of pieces of lines. So if I'm going to graph the slope graph to this velocity graph, let's take it a piece at a time. So I'm going to start down here at 0, 0. Okay, this first piece ends up here at 1, 3. Okay, well, what's the slope of that piece? Well, it has a constant rate of change. You have labels on the axes. So count, rise over run. Delta y over delta x. I'm going up 3 and running 1. So rise over run, 3, a slope of 3. So no matter where you stand from 0 to 1, the slope of that graph is always 3. So coming down here to produce the acceleration graph, it's easy when you have piecewise linear function. Okay. So I'm going to go ahead and get on here some tick marks. Okay, and now I know that on the time interval from 0 to 1, my slope is 3. So I'm going to have a horizontal step here. I'm going to close the left, and now above 1, vertically above 1, I'm going to put an open circle. And then I'm going to connect the points in between with a little horizontal step. Anywhere on that time interval from 0 to 1, I have a slope of 3. Let's find the next piece. All right, so the next time interval begins at 1. It looks like it falls all the way underneath the x-axis. So the next piece starts here and ends here at 3, -2. Oh, this is great. Oh, I was hoping it would be gone. All right, let's look at this slope. Well, I'm dropping 5 and I'm running 2. So that tells me that my slope is -5/2 on the time interval from 1 to 3. So -5/2, I'm going to just make that -2.5. So -1, -2. Oh, not good. -3. So, okay, come back. Okay. So -2.5 would be about right here. So lining up with 1 vertically, open circle, all the way across to 3. Conclude this step, okay, with another open circle, connect. Okay, you do know there's an x-axis there. Okay, so that's going to be the constant rate of change on the interval from 1 to 3. Okay, so now let's go back up. Let's look at the next piece. Okay, well, my next piece from 3 to 5 is horizontal, so the slope is 0. So open at 3, open at 5, connect, and that's the slope of the graph. Okay, the next piece. It appears that on the original graph, it went from 5 all the way over to 8. So if I counted rise over run, I think that's a slope of 1. So from 5 to 8, it's a constant rate of change of 1. Open circle at 5, 6, 7, 8, open circle, connect. So we're going to have a series of steps, if you will. Okay. All right, and then from, I guess I can look at the speed graph up here. From 8 to 9, that appears to be a negative, I think it's a -1. So -1 would fall about right here, 8 to 9. And then from 9 to 10, we know it's another constant rate of change of 0, so it looks like this. So notice that my final acceleration graph is closed on the left endpoint, 0, closed on the right endpoint, 10, but everywhere else it's open. The reason being, if you think about it, okay, look back at your velocity graph. Let's kind of look at this one. I know what the velocity graph looked like here, but using the speed graph so I don't scroll back up, the slope on this side is 3. The slope on this side is -2.5. Well, if I asked you what's the slope at that sharp turn, I'm hoping you say it doesn't exist. So that means that I don't want to connect these, and I certainly don't want to close one of them. I want to leave both of them open just to indicate that the derivative does not exist. So when your graph consists of lines, it's piecewise linear, as this given velocity graph was, and you're asked to produce the slope graph, then you know that your answer will be a set of steps, horizontal steps such as this. So if you're starting with linear pieces, you're going to have horizontal steps like this for the slope graph. So hope this helps.